Good morning, students. This is second class on surface chemistry. Presently, we have to take up the topic that is the colloidal solution. Clear? Topic for today's class is colloidal solution. Very true that primary idea pertaining to colloidal solution was given to you in your class 9 only. Please remember that we have to read about what is true solution, what is another kind of solution that is known as colloidal solution, and still another kind of solution that is suspension. So these are three broad classification of solutions depending on particle size. Depending on particle size. Important point here is that okay, wait for. So this is surface chemistry, part 2. Topic is colloids, what we also call colloidal solutions. One thing is clear that colloids are also solutions. Only thing is that this is a different kind of solution from ordinary solution, what we call true solution. Okay, one thing, simply just to introduce to you basic ideas. This is true solution. This is colloidal solution, and this is suspension. We are trying to differentiate. In true solution, colloidal solution, and suspension. These are three different kinds of solution based on particle size. This is an important point. I think this entire topic is based on this very important idea of particle size. See, true solution, in case of true solution, particle size is less than 1 nanometer. Less than 1 nanometer. You know, 1 nanometer is equal to 10 raised to the power minus 9 meter. Okay. So in case of a true solution, one example you can take. Okay, common salt sodium chloride you dissolve into water. Okay, this makes a solution. This is an example of a true solution. Many such solutions you have which can be categorized as true solution. Okay. Now, in case of colloidal solution, particle size is greater than 1 nanometer. Particle size of colloidal solution is greater than 1 nanometer. Particle size of colloidal solution is greater than 1 nanometer but less than 1000 nanometer. 1000 nanometer. So, particle size falls in between 1 nanometer and 1000 nanometer. Particle size is larger than 1 nanometer but smaller than 1000 nanometer. Okay, so coming to examples of colloidal solution, we have several examples. Your blood is a colloidal solution. Milk is a colloidal solution. Shaving cream is a colloidal solution. Boot polish is a colloidal solution. Clear? There are several examples we will come across. Now we are coming to suspension. Suspension is also a kind of solution in which particle size is larger than 1000 nanometer. Very simple. Okay, earlier we used to write on the blackboard or green board with the chalk pencil. Okay, if that piece of chalk is dissolved into water, you will notice that chalk particles are dispersed throughout the solution. But it's not a true solution, nor it is a colloidal solution. Rather than this is a suspension, because after some time you will find that although chalk particles have settled down in the beaker, suppose you had your chalk powder solution, okay, kept in a beaker. After some time you will find that those chalk powder which were initially found to be scattered, dispersed throughout the solution, is now settling down after some time. Okay, so that is an example of suspension. The main difference is particle size. In terms of particle size only, the best kind of distinction is made. Other points are also there which will distinguish true solution, colloidal solution, and suspension. Okay, this another thing is homogeneous or heterogeneous. Homogeneity or heterogeneity, that is whether true solution is homogeneous or heterogeneous. This is homogeneous, and both these colloidal solution and suspension are heterogeneous. Milk, it looks like as if it were a homogeneous solution, but in fact, if seen through ultramicroscope, this has been found that milk is a heterogeneous solution. Suspension is also heterogeneous solution. Okay, there are other points to distinguish. Okay, this is homogeneous, heterogeneous. So this is point number 1. This is point number 2. Okay. Another thing is a very important thing, that is what we call Tyndall effect. Tyndall effect. This is a kind of optical phenomenon, that is related to light. Okay. In case of colloidal solution, if light is passed through a colloidal solution in a dark room, if light is passed through the colloidal solution in a dark room, you will find that the path of propagation of light becomes visible. Path of propagation of light becomes visible if light ray is allowed to pass through a colloidal solution. If light is visible, then this phenomenon is known as Tyndall effect. Tyndall effect is nothing but visibility of the light ray when passed through a colloidal solution. Clear? I hope you have understood. Now somebody can ask, what's the reason? Why the path of the propagation of light becomes visible? For that thing, the the basic reason is that light rays are scattered. By these colloidal particles. This is due to a scattering of light. Scattering is an optical phenomenon. You know, a scattering is an optical phenomenon. So this Tyndall effect is due to a scattering of light by the colloidal particles. Tyndall effect is due to a scattering of light by colloidal particles. Okay, so what is Tyndall effect? Simply speaking, when a light ray passes through a colloidal solution, the path of propagation of light becomes visible. This is known as Tyndall effect. This is observed in case of colloidal solution. This Tyndall effect is not observed in case of true solution. Okay, and here in case of suspension, this may be observed, may not be observed, may or may not. All these things happen due to particle size. Okay, appropriate particle size for a scattering of light falls within this range. I mean that particle size should be larger than 1 nanometer, but smaller than 1000 nanometer. Okay, clear. So these are basic differences, and we are classifying here solutions into three types, into three parts. One is true solution, another is colloidal solution, another is suspension. Okay, another is Brownian motion. Brownian motion. Okay, this has been found. This has been found that colloidal solution, in a colloidal solution, colloidal particles are in Brownian motion. Colloidal particles are in Brownian motion, that is, they adopt zigzag path, irregular path, something like this, something like this. Something like this. This is zigzag path. So colloidal particles have zigzag path in a colloidal solution that has been seen through ultra microscope. And reason why this happens, because there is a continuous bombardment, prahar, striking. There is a continuous bombardment of dispersion medium. Okay, water may be a dispersion medium. Okay, alcohol may be dispersion medium. If water is dispersion medium, that is hydrosol. If alcohol is dispersion medium, that is alcohol. Okay, so continuous bombardment of dispersion medium over colloidal particles causes Brownian motion. That is irregular path of movement of colloidal particles, zigzag path. Is it clear? So Brownian motion has been found in case of colloidal solution, not in true solution. Okay, these are the things. Even for suspension also, Brownian motion can be observed, cannot be observed, both the cases, depending on how large the particles of suspension is. Okay, so these are several things based on which we distinguish between three classes of solution: true solution, colloidal solution, suspension. The most important point is particle size. All other points depend on this particle size. Due to the difference in particle size only, true solution, colloidal solution, and suspension are regarded to be different types or different class of solution. Okay. Now we are trying to classify colloidal solution. Now, colloidal solution may be of different types. Once we have seen that solution may be of three types, it may be true solution, it may be colloidal solution, or it may be suspension. Now, what I say even colloidal solution can be classified in various ways. Classification of colloidal solution. One is what we are taking up here based on particle size. So colloidal solution may be classified into three types. Point number one, this is multimolecular. Multimolecular colloids. Another is macromolecular colloids. And still another is associated colloids. Dear children, what I understand is that you should be able to understand the meaning of the word. Understanding the meaning of the word helps us interpret the ideas in a comprehensive manner. We can understand it. Multimolecular colloids. Multi means what? What is multi? Multi means many. Okay. Molecular stands for molecules. So multimolecular means many molecules. Many molecules. Okay. The idea is multimolecular colloids. Okay. This be these are many molecules we have taken. Okay, let it be gold particle. Gold particle. Gold particle. So many molecules, say a gold particle aggregates. Aggregate to form, suppose, a single molecule. Different molecules aggregate together to form a single molecule, the size of which falls within colloidal range. The size of which falls within colloidal range. This means here the size is less than 1000 nanometer and greater than 1 nanometer. Simply speaking, what I have told, a large number of molecules aggregate together to form a single molecule, the size of what? The size of this single molecule formed falls within colloidal range. What is colloidal range? This is colloidal range. 1 nanometer to 1000 nanometer. Less than 1000 nanometer, larger than 1 nanometer. Okay. Therefore, such kinds of colloids or colloidal solution is known as multimolecular colloids. Multimolecular colloids, how can you define it? Very simple. Okay. So many molecules, a large number of molecules aggregate together to form a molecule, the size of which falls within colloidal range. Okay, if such kind of colloidal solution is known as multimolecular colloid. Okay, so many examples are there. Gold sol. Okay, the most general type of colloidal solution. Okay, based on the nature of physical state of the dispersed phase and dispersion medium, will classify colloids into different types, one of which is what we call SOL, S-O-L. Okay, here what is dispersion medium is liquid. Dispersion medium is liquid and dispersed phase is solid. Okay, you'll say what is dispersion medium, what is dispersed phase. Certainly you should ask, you should know it very well. Okay, you can take analogous case. Okay, we have a true solution. Okay, we have a binary true solution. Binary true solution, that means only two components. Bi means 2, bi means 2, bi means 2. Binary solution has only two components, so presently we are considering a binary solution. Okay, in a binary solution, one will be solute, another will be solvent. Okay, so in case of a true solution, a binary true solution, we have two components, solute and solvent. Exactly in the similar fashion, similar manner, in a colloidal solution, okay, two components, what we call solute in a true solution is known as dispersed phase in a colloidal solution, and what we call solvent in a true solution is known as dispersion medium. Okay, this is a very simple understanding. For dispersed phase, we'll say this is dP and dm. Okay, for our purpose, this dP stands for dispersed phase and dm stands for dispersion medium. Okay, so that is multimolecular. So what is multimolecular colloid? Coming back to so many molecules aggregate together to fall within colloidal range. Very simply speaking, once you understand, you can write it the either way, any way you wish to write. Okay, there is no hard and fast that you should write this definition or that definition. Only things should be clear, things should be understanding should be vivid, understanding should be crystal clear. You can write in your own language so many molecules aggregating together to form a particle, the size of which falls within colloidal range. That is, it is less than 1000 nanometer, larger than 1 nanometer. So many examples: gold sol, okay, platinum sol, okay, sulfur sol. These are all examples for multi-molecular colloids. Okay, so based on particle size, we are trying to classify colloidal solution. Okay, fine. Next, we are coming. This is macromolecular colloids. Okay, again, I wish you to understand what is the meaning of macro. Macro means very large. Macro. Okay, there are two things: micro, very small; macro, very large. Here, what is the title of this class of colloids? Macromolecular colloids. Macromolecular colloids means this kind of colloidal solution is made up of macromolecules. This kind of colloidal solution is made up of macromolecules. What are examples for macromolecules? Examples for macromolecules are proteins, okay, even carbohydrates, proteins, okay, starch, that is carbohydrate only, starch is a carbohydrate, okay. These things, they are large molecule, you know, they are made up of by polymerization, they are very large number of molecules aggregating, getting polymerized into one large giant molecule, therefore polymers. They are macromolecular, starch, protein, etc. They are known as macromolecules. Okay, and in such kind of colloidal solution, macromolecules work as colloidal particles. Their particles, macromolecular colloids, their particles match with the size of colloidal particles. That is, the size of colloidal particle in a macromolecular colloids fall within colloidal range. Okay, so these large molecules, okay, disintegrate. Such large molecules, there we told aggregation, here we are telling disintegration, just opposite process. So this large molecule disintegrates to assume what colloidal size, to assume colloidal size. So okay, macromolecular colloids, large molecules, they are aggregate, they are disintegration, they are disintegrating, this is macromolecules. So large sized macromolecules disintegrate into particles, the size of which fall within colloidal range. Okay, examples are, okay, Examples are starch sol, protein sol, all that are examples of macromolecular colloids. Okay, dear children, now we are coming to associated colloids. Associated colloids, very famous example, soaps and detergents. Okay, they are soaps and detergents. They are examples for associated colloids. Okay, they are surface active agents. Okay, surface of soap molecule and detergent molecules are very active. They are the examples of associated colloids. Okay, there we have examples. We have examples when a particular electrolyte, okay, at low concentration, at particular solution in which certain electrolytes are there, they are at low concentration. They do not make alkaloid, but at large concentration, at higher concentration, what happens? Particles aggregate to form what we call micelle. What we call micelle. This was taught in class 10. This type of things, such kind of figure, radial structure you have seen. Radial structures you have seen. Okay, here negative, that is the hydrophilic part project outward, and this hydrophobic part project inward. This is so many soap particles are aggregating together. Okay, in general, what do we write? RCOONA. This is soap molecule. Okay, this is higher alkyl group. Only difference is that sodium salt of higher fatty acid, that is soap. Okay, this may be C15S31. This is a higher alkyl group. Total number of carbon atoms here in this alkyl group is 15. Okay, it's not methane, ethane, propane, butane like that. This is C15. Okay, H31 COONA. This is known as sodium permeate. Everybody knows. So, if solution of this thing, at low concentration, this is simple solution. But at higher concentration, what happens? All these particles aggregate together to form the micelle. Therefore, they aggregate together, they associate together. Hence the name associated colloids. Okay, so at large concentrations, so many particles are associated, so many electrolytes are getting associated at large concentration, mind it, and above a particular temperature, that is known as Kraft temperature. That is known as Kraft, K-R-A-F-T. That is known as Kraft temperature. Beyond a particular temperature, only so many soap molecules are associating together to form a micelle, to form a radial structure. Radial structure means spherical. This is a spherical kind of things. Therefore, what we call a radial structure, this is also known as micelle. M-I-C-E-L-L-E, micelle. Okay, micelle formation. So this micelle formation takes place, this association of soap particles takes place at higher concentration and beyond a particular temperature. That temperature is known as Kraft temperature. And for micelle formation, there should be a minimum concentration, that is known as CMC. This is critical micelle concentration. Critical micelle concentration, and that is after a certain concentration only micelle formation takes place, associated colloid is formed. Okay, the size of such micelle is within colloidal range, is within colloidal range or in colloidal range. So above a particular concentration only micelle formation will take place, that is associated colloids will take place. Okay, and beyond a particular temperature, that is Kraft temperature. That is Kraft temperature. So in order that associated colloid is formed, two things are important: critical micelle concentration and Kraft temperature. Okay, so beyond a particular temperature only micelle formation will take place. That temperature is known as Kraft temperature, and beyond a particular concentration only micelle formation will take place. That is known as CMC, that is critical micelle concentration. Okay, so associated colloids, we can take examples: soap and detergents. Cleansing action of soap is based on this micelle formation. Okay, we will not go into that. You know that what. So this COO minus Na plus part is polar in nature, positive and negative charge. Therefore, this is polar in nature. Polar in nature. So this part attracts water molecule. While this hydrocarbon part C15S31 for that matter, in this example, this is hydrophobic, water repelling. Water repelling. Water repelling. Okay, so what happens? Oil, grease, all that are trapped. The oil, grease, these are organic moieties, organic compounds. So they are trapped within this area. Okay, within this area after agitation. After agitation, hilorne ke baad. Okay, and these water molecules get attracted towards this polar part of a soap molecule in the micelles. Okay, so the outer parts are polar part, this part is polar part, and this part is inner part towards the end, inner part. This is hydrocarbon part, hydrophobic. So cleansing action is based on this micelle formation. Okay, so based on particle size, we have three different types of multimolecular colloids. Three different types of colloids. They are multimolecular colloids. Another is macromolecular colloids, and another is associated colloids. Okay. Now, dear children, after doing all these things, I understand that you can browse through your textbook yourself. Okay, comprehensive notes we have already provided you. Wheresoever possible, we provide you notes, and you are required to browse through, read out properly, try to understand. Okay, take it a task on your own that we have to understand what this is. Unless you are eager, you intend to learn, nothing can be done. Okay, that you know, you are quite mature now to understand all these things. Now that classification of colloids is not over. Classification of colloids is not over. What happens? We have considered based on different physical properties, we classify the things. Different properties, we classify the things. So here, particle size is the property based on which we have classified colloidal solution. Okay, and another may be whether a particular colloidal solution is solvent attracting or solvent repelling. Based on this issue, a colloidal solution has been classified into two parts. Okay, based on the fact whether a particular colloidal solution is solvent attracting or solvent repelling. Colloidal solutions have been classified into two parts. They are lyophilic, Lyophic, lyophilic, lyo means solvent. Lyo means solvent. Lyophilic. So simply speaking, just in brief, I'll tell you this lyo means solvent. Philic means lyo. Together, this is lyophilic, solvent loving. Another may be lyophobic, solvent repelling. So, based on the idea whether a particular colloidal solution is solvent loving, solvent attracting, or solvent repelling, a colloidal solutions may be classified into two parts, that is lyophilic colloidal solution and phobia repelling. Okay, hating, lyophobic. Okay, if water be the solvent, what we call dispersion medium in case of a colloidal solution. So if water be the dispersion medium, okay, that is solvent, water be dispersion medium, then instead of lyo we can write hydro. Hydro stands for water, hydrophilic, that becomes, instead of lyo again we can write hydro, so that is hydrophobic colloidal solution. That means hydro because here solvent is water. In general, lyo, any other suitable solvent may be taken, any other suitable dispersion medium may be chosen. Okay, so lyophilic and lyophobic colloidal solutions are two different types of colloidal solution based on whether the given colloidal solution is solvent loving or solvent repelling. Okay, clear. So many things are there. Like this lyophilic colloidal solution is reversible. Lyophilic colloidal solution is reversible. That means, okay, if colloidal state is broken, okay, colloidal state is broken, it gets precipitated, it doesn't remain dispersed. Colloidal particle, dispersed phase particles do not remain dispersed in the given dispersion medium. Okay, dispersed phase all settle down. That means coagulation has taken place or precipitation has taken place. That means colloidal state has been disrupted. Colloidal state is broken. Colloidal state doesn't exist. Okay, in that case, suppose again dispersion medium is added, then what happens? What happens? Again, colloidal solution is formed. That means, because this is simply because this is solvent loving, solvent attracting, it is for that reason, with the addition of dp plus dm, dp for dispersed phase, dm for dispersion medium, okay, other conditions, other parameter, temperature, all that. This is colloidal solution, and back, this is we can write plus dm upon adding dispersion medium, immediately colloidal solution is formed, and from this colloidal solution, if we remove dispersion medium, then what happens? dp is precipitated, and again if you add dispersion medium, immediately colloidal solution is reformed. That means this is a reversible process. This is a reversible process. So lyophilic colloidal solution is reversible. On the other hand, lyophobic one is irreversible. Lyophobic is irreversible. Once colloidal state breaks, it cannot reassume its colloidal state upon addition of dispersion medium. But in case of lyophilic colloidal solution, what happens? Okay, if colloidal state is disrupted, is broken, okay, then what happens with the addition of dispersion medium again? With the addition of dispersion medium again, we can bring the solution into its colloidal form. It is for that reason lyophilic sol is reversible. Okay. Lyophilic is highly stable. Lyophilic is highly stable. Okay, suitable dispersion medium you need to have. Dispersed phase you need to have. You mix them. Okay, what happens at proper temperature? A colloidal state is formed. Colloidal state is formed. In which colloidal state is formed, that means that solution in which particles are within colloidal range. Okay, these are the things. We'll understand all these things again. Other methods of classification. Half of this colloidal issue, colloidal solution topic is understanding classification of colloids and another few things, certain properties of colloidal solution, like we have talked, Tyndall effect. Again, we can talk about electrophoresis, Brownian motion, all that in pretty detail. Whatsoever we have to understand at class 12 level. Okay, and then properties of colloidal solution and why and charge of colloidal particle or charge of colloidal solution. Okay, so these things are important issues. We will take up purification of colloids also, dialysis and electrodialysis. Okay, these are the things still we have to do. Hope for the best. Keep reading. I will provide you notes. I have already provided you notes. Okay, thank you. Thank you all. Thank you.